Bien, buenos días a todos. Ahí está, bien, gracias. Bien, en nombre del rector y de la Universidad de Santiago de Compostela tengo el gusto, el honor de presidir este acto preámbulo de la conferencia que impartirá nuestro querido invitado, Sir Michael Atiyah, receptor, como ya saben todos ustedes, de reconocimientos como la Medalla Fields 1966 y el Premio Abel 2004, siendo ambos los máximos galardones en el mundo de las matemáticas. Bueno, antes de nada decir que el rector lamenta no poder estar aquí hoy en este acto de presentación y que me ha pedido que les transmita un afectuoso saludo. Bien, a continuación me gustaría pasar a presentar a las personas con quienes tengo el gusto de compartir esta mesa. Por supuesto, a mi izquierda tengo a Sir Michael Atiyah, el gerente del consorcio de Santiago, José Manuel Villanueva, el decano de la Facultad de Matemáticas, Juan Viaño, y el comisario del programa ConCiencia, Jorge Mira. Bien, y en primer lugar tiene la palabra el señor don José Manuel Villanueva, gerente del consorcio.
Moi ben, moitas gracias. Eu vou ser moi breve porque, evidentemente, estamos aquí para escoitar unha conferencia do profesor Atiyah e non outro tipo de intervencións. Simplemente indicar que o consorcio é un organismo que leva 15 anos de vida, que é un organismo no cal se reúnen as administracións do Estado, da Comunidade Autónoma e do Concello de Santiago para levar adiante basicamente dúas actividades: a protección patrimonial da cidade histórica e o da dinamización turístico-cultural tamén da cidade. Ben, neste contexto, precisamente neste ano, se tomou a decisión de entender que o mundo da cultura, que até o momento estaba circunscrito nas actividades fundamentalmente organizadas polo consorcio, do que é a cultura orientada máis ao mundo artístico. Evidentemente, a ciencia é unha componente fundamental do elemento dunha concepción da cultura. Entón, parecía interesante facer unha experimentación que era precisamente este programa ConCiencia, que creemos sinceramente que é unha iniciativa que está tendo unha acollida o suficientemente interesante como para que se poda consolidar en anos vindeiros e que dé tamén de cara a fora o perfil que a cidade de Santiago ten, que non é exclusivamente unha cidade con grandes riquezas patrimoniais e con unha significación espiritual indiscutible, senón que tamén é unha cidade na cal a ciencia ten o seu espacio e unha parte, diríamos, fundamental da vida urbana. Entón, neste sentido, este é o programa. Agradecemos moito a colaboración da Universidade para poder levar adiante esta iniciativa, que evidentemente sen a súa colaboración sería imposible, e especialmente a Jorge Mira, que é o comisario que, diríamos, encargou durante este ano de levar adiante este proxecto, que confiamos, repito, que o ano que ven teña continuidade e que acabe sendo algo que no futuro poda ser parte, diríamos, da tradición e do patrimonio histórico tamén da cidade de Santiago. Nada, moitas gracias.
Bien, gracias. Bueno, pues yo personalmente y como vicerrectora de investigación he de decir que, por supuesto, este es un acto que es motivo de orgullo para nuestra universidad y no puede ser de otro modo contando con la presencia de científicos de la talla como es Sir Michael Atiyah. Por ello, una vez más, hemos de aplaudir y de apoyar esta iniciativa del Consorcio de Santiago para promover la divulgación científica a través de este programa ConCiencia, que nos consta que ha sido de muy alto éxito. Programa que nos ha permitido presentar, acercar a no solo a nuestra comunidad universitaria, sino también a nuestra sociedad, figuras de tan alto nivel de todos los ámbitos científicos. Este es además uno de los compromisos que ha adquirido el actual equipo de gobierno, avanzar en lo que es la proyección exterior y la divulgación de la investigación. Creemos que, en efecto, esta es una tarea que conjuntamente con el Concello estamos llevando adelante, entre otras, con esta iniciativa. Bien, el profesor Mira nos presentará a continuación el perfil de Sir Michael Atiyah. No voy a entrar en detalle porque él es el que le corresponde esta presentación, pero por supuesto decir que sentimos hacia él un gran respeto y admiración. Y por supuesto es gracias a científicos de la talla de Sir Michael Atiyah a quienes debemos en gran medida nuestro bienestar social y cultural. Y en este sentido creo que las matemáticas representan, como es sabido, la raíz de la ciencia y un motor imprescindible, fundamental para el desarrollo. Y también he de decir con orgullo que la USC representa un exponente claro en la investigación en el ámbito de las matemáticas, tanto a nivel nacional como internacional. Simplemente a título de ejemplo, que prueba la notoriedad de nuestros matemáticos, basta con destacar la celebración reciente de la Asamblea Internacional de Matemáticas, siendo dicha asamblea la que decide la comisión que asigna las medallas Fields, que como todos sabéis son, y decíamos antes, el más alto galardón en el campo de las matemáticas. Bien, no quiero prolongarme más tiempo porque es sin duda a él a quienes vienen a escuchar y él es nuestro invitado de honor. Y quiero finalizar mi intervención antes de darle la palabra al profesor Jorge Mira, simplemente dirigiendo unas palabras de agradecimiento a nuestro invitado. Sir Michael Atiyah, on the behalf of the Rector and the University of Santiago de Compostela, I would like to thank you very much for coming here, for visiting our university. It is a great honor for us to have you here with us. Thank you very much. We wish you a very pleasant stay in our university, in our home, and in the city of Santiago. Thank you very much. Y nada más, a continuación tiene la palabra Jorge Mira.
Estimada señora vicerreitora de Investigación e Innovación, ilustrísimo señor xerente do Consorcio de Santiago, ilustrísimo señor decano da Facultade de Matemáticas, profesor Atiyah, donas e cabaleiros, o programa ConCiencia ten varios obxectivos. Por unha banda, achegar líderes mundiais da ciencia ao tecido investigador da USC. Por outra, realizar un labor divulgativo, tanto dos grandes pilares do coñecemento científico como da actividade punteira da nosa universidade. Por exemplo, do excelente papel desenvolvido pola casa que hoxe nos acolle na organización da Asamblea Xeral da Unión Matemática Internacional, máximo organismo regulador da matemática no mundo. Aproveito a ocasión para felicitar tanto ao señor decano como un antigo membro desta facultade, o profesor Manuel de León, polo seu ingreso na elite de 10 membros que conforman o comité executivo dese organismo. Pero no fondo de todo isto, o programa ConCiencia pretende homenaxear o talento e a intelixencia en estado puro. Tal é como deixa entrever o noso logo. Concienciar a cidadanía de que nun mundo en crise de valores, a creación intelectual é a manifestación suprema da natureza humana e que debe ser recoñecida e valorada como tal. Que mellor exemplo de extraordinario talento e intelixencia que o noso invitado de hoxe. O profesor Michael Francis Atiyah é simplemente un xenio. A súa obra ocupa os cumios da historia da matemática dende os anos 50 ata a actualidade, sen interrupción. Iso conleva que sexa considerado como un dos principais xeómetras do século XX. E dada a cantidade e calidade da súa obra ao longo dese máis de medio século de actividade, o matemático vivo máis importante do mundo. Logo da súa tese de doutoramento na Universidade de Cambridge, viñéronlle fructíferas etapas no Instituto de Estudos Avanzados de Princeton e nas universidades de Oxford e Cambridge novamente, que derivaron en espectaculares resultados. A demostración do teorema do índice, un resultado que serviu para desenvolver varias áreas da matemática dende entón. A xeneración da teoría K topolóxica, unha das principais ferramentas da topoloxía algebraica e que conduciu a moitas aplicacións á física e a matemática. Precisamente a creación de pontes entre a física e a matemática é, sen dúbida, un dos seus factores diferenciais. Co traballo xa mencionado e coa demostración do teorema de punto fixo, creou liñas de traballo na teoría da representación e na chamada ecuación de calor dos múltiples. En fases posteriores, adentrouse en teorías Gauge, variedades algebraicas, análise complexa, e nas teorías Gauge, en particular na teoría de Yang-Mills, onde abriu camiño para o traballo de outros destacados persoeiros como Witten. Hoxe en día está traballando en teoría de supercordas. Por tales resultados, e outros moitos que non menciono, recibiu os máis importantes galardóns. A Medalla Fields en 1966. Como sabedes, non hai Premio Nobel, e esa é a maior distinción que pode ter un matemático. Como aquí hai moito matemático, se queredes levala, tedes que ter menos de 40 anos. Tamén levou outro galardón de semellante importancia, que foi o Premio Abel, outorgado pola Academia Noruega de Ciencias, textualmente polo descubrimento a proba do teorema do índice, vencellando topoloxía, xeometría e análise, e o seu destacado papel na construción de novas pontes entre a matemática e a física teórica. Aínda hoxe en día, aos 77 anos, Sir Michael Atiyah continúa en liña de vanguarda da física teórica e a matemática, demostrando un talento a todas luces prodixioso, con artigos de referencia obrigada en varios campos da física e matemática nos últimos 4 anos. A marxe da súa actividade puramente científica, foi tamén fortemente activo na organizativa. No tocante ás matemáticas, podemos citar, por exemplo, a súa creación do Instituto Isaac Newton de Ciencias Matemáticas en Cambridge. Foi presidente da Royal Society e tamén é o gran impulsor da Sociedade Matemática Europea. A nivel xeral, é fundador do panel interacadémico de asuntos internacionais, unha rede global de academias científicas de todo o mundo. Para rematar, quero facer unha mención especial de outra actividade que ten, que é a actividade humana. En este caso, a súa presidencia das conferencias PUGWAS. Esas conferencias son unha organización internacional fundada por Bertrand Russell e o Nobel da Paz Joseph Rotblat, no inicio da tensión nuclear dos anos 50 ao abeiro do manifesto Russell-Einstein, e que alertaba daquela do gran risco que existía de confrontación nuclear. Son datos que nos indican que neste caso a calidade intelectual vai parella coa calidade humana. Sir Michael, it's a great pleasure to have you here. For me, it's an honor to be with you all these days, and I'm sure that you will give us an excellent lecture. Thank you.
For the first time in Santiago to visit your beautiful old city and also your university, and to see here so many young people in studying mathematics, physics, and other things. This talk is part of a general program covering many areas, and my talk is addressed to a general audience about mathematics, but not too much detailed mathematics, no difficult examinations. And my title, my talk, is about the question in mathematics, whether mathematics consists of discovery or invention. Now, mathematics lies between, it's not a science exactly, it's partly way between science and the arts. And the relation with science is, of course, well known, and the great names of science like Newton, Maxwell, Einstein use mathematics to lay down the fundamental equations of physics. But mathematics also has links with other fields. In particular, it has a link with philosophy through the fact that mathematics is based on logic, logical reasoning, and philosophers have always been interested in the nature of logic and its implications. And for example, way back in the time of the Greeks, Plato was a philosopher, of course, and he was very interested in mathematics. He philosophized a lot about mathematics. And as you heard, Bertrand Russell's, whose picture appeared behind me just now, he was a famous mathematical logician and a philosopher. But mathematics also has links with any other areas, not a part of philosophy, but part of the arts. If you think about painting, then the discovery of perspective in the Renaissance was a great step forward in the development of painting. So painting has a mathematical, geometrical aspect to it. Music, harmony in music is of course based on the musical scale, which has a mathematical basis, and music in many ways is an abstract, artistic form of mathematical representation. Architecture is of course about putting buildings, and buildings to be beautiful have to have certain proportions and ratios, and architecture is in many ways a very obvious example of application of geometry into three-dimensional buildings. So all of these aspects of connection with art show you the relationship between mathematics and things that we regard as beautiful. And beauty plays an important role in mathematics, which is not always understood by people outside. How can something like mathematics be beautiful? Well, I hope to try to explain that a little bit in my talk. Beauty is a very important part of mathematics. So, mathematics is part art and part science. Now I come to the question of its relationship to the physical world. In general, do we discover what exists in the physical world? Do we find out for ourselves how the world works? Or is it perhaps an ideal world, or Plato's Platonic world, or ideas? And do we invent the Platonic world? Do we create it ourselves? Or have we discovered it outside? This is the question that has wondered philosophers for thousands of years. David Hume, Immanuel Kant, and others have discussed to what extent we discover things outside and to what extent we create them in our mind as a picture of the outside world. And these deep philosophical questions, which go on for centuries, are not questions that have a yes or no answer. They are questions that you need to think about. And it is evenly balanced on both sides. And so instead of discussing this in an abstract philosophical form, I think it's better to consider elementary examples. The best philosophers, I always used to like reading Bertrand Russell's philosophy, because he always gave examples in very simple terms of the philosophical problems. Then you could understand what he was saying. I think he was the only philosopher I could understand. I recommend you to read him if you haven't read him. So I want to consider elementary examples to illustrate my points. Now, there's one very simple remark I can make at the beginning. What is the distinction between an invention and its discovery? Well, if you're commercially minded, an invention can be patented and you can become rich. A discovery cannot. So if you discover, like Newton, the laws of gravity, you don't make any money. Maybe you should change the rules there, but that's the way the law is set up. So a discovery is something you find out about nature. It was there before. You cannot claim credit for it. You cannot patent it. And actually, this question of what is patentable and what is not patentable is a very concrete illustration of the important philosophical questions. Because in the modern age, with the advances in science, this question becomes much more complicated to answer. And the whole discussion about the human genome, what is a gene? Do we discover it? Do we patent it? Find about it, invent it? And the question about what you can patent in the world of molecular biology has become a highly controversial problem, which raises big issues of international politics and finance. So these are very practical questions, and philosophical questions sometimes have practical implications. Now let me go to my first set of elementary examples, and I will take them first of all from the field of geometry. So let me start with some elementary examples about what are called the Platonic solids. These are the regular shapes which are known to Plato, which start off with the tetrahedron, which has 4 triangular faces, the cube, you know, and then more complicated ones like the octahedron, which consists of a thing with 8 sides, a pyramid on top and another pyramid underneath. Then the more difficult ones, which I can't draw, the dodecahedron, and if your Latin is good enough, you work out what that means. It means it has 12 faces, which are actually pentagons, and it has 20 vertices. And then the icosahedron is a sister solid, which the numbers are reversed. It has faces which are triangles. There are 20 of them. And on the column over on the right, I've given the numbers of vertices, edges, and faces of these famous regular solids. Now, before I go on, let me make a comment about history. These are called the Platonic Solids. They were known to Plato. Plato wrote about them. They were known a bit before Plato to the Greeks. But I only discovered recently, and I now live in Scotland, that stone models of these regular solids, made with very crude implements but beautifully shaped, can be found in Scotland as far early as 2,000 years before Christ, long before Plato or any of the Greeks came along. So in an era which we think of as probably the Stone Age, literally, they were really in the Stone Age civilization, there was somebody clever enough to invent or discover the icosahedron. Of course, the cube is something you can see around lots of natural things in the form of cubes. Perhaps the tetrahedron you can see in some forms, occasional crystal forms, but the icosahedron does not exist as a natural object. And it's a very complicated one to make. If you ever tried with models, it's not easy. So the first person to actually identify the icosahedron, he was a mathematical genius, and he may have been a primitive savage by our standards, but he was actually an advanced mathematical thinker well over 1,000 years before Plato. I was very interested to find this out in Scotland, and I thought there was there are in the museum, you can see these, and I thought, who was it made this discovery, what were they used for? I made inquiries to my friends who are archaeologists, and they said there are hundreds of copies of these stones all over Scotland. So they played some important role in the society at the time, religious, mystical, or symbolic of power. Nobody knows, but there they are, hundreds of them, and they're, Now, this is Scottish propaganda, of course, and it may well be that here in Galicia, your archaeologists can find similar ones, even older. I asked, let us have some friendly competition, see what the people here in Spain were doing 2,000 years before Christ. Well, let's leave aside the history. Going back to the elementary mathematics, one of the things you can notice about the numbers of vertices, faces, and edges of these solids is they all satisfy a simple formula. The number of vertices minus the number of edges plus the number of faces is always equal to 2. You can easily check it from this list. This formula was known as Euler's formula. It was noted by the famous mathematician Leonhard Euler, 18th century. It's also true, the figures do not need to be at all regular like this. If you make more complicated shapes on the surface of the sphere, of any kind, with any number of mixture of different kinds of faces and so on, you always find this number is equal to 2. It's a very remarkably robust formula. And it turns out to be a very important formula. It's the first example of a formula of what you call topology, something which doesn't change when you change lots of things. It's very rigid, very robust. And it turned out to be important in modern mathematics. And it was discovered by Euler. Well, the question is, did he discover this formula, or was it invented? Did he find the formula by looking experimentally, or did he work it out as a piece of mathematical thinking? So there's the first example where the answer, a question you can ask, and the answer is not obvious. Now let me move from geometry to something even more elementary. Let us look at where mathematics starts, the integers. 1, 2, 3, 4, 5, 6, etc. Now, the question is, did we discover these or were they invented? Well, the famous German mathematician Kronecker, who was a very extreme purist, he said the integers were created by God, all else by man. So he took a very clear line. God made the integers, man did the rest. That's an extreme point of view. But even if you take that point of view, I've started the integers with 1. But some people would say the integers start with a 0. I mean, a 0 is, in many ways, a very important integer. But you don't find it anywhere. It's not there. There's nothing to find. But you see, when you go beyond numbers like up to 1, 2, 3, up to 7, as you know, to write bigger numbers down, we need the good notation. And the Romans, for example, had a very bad notation, all those V, X's, and L's, which you can never work out whether it's the 17th century or 16th century. The decimal notation, which came from India and the Arabs and probably through Spain, is of course much better. But the decimal notation, you couldn't possibly do it without using a zero. So the zero is actually a very important part of the integers. And well, even if you don't use the decimal notation based on 10, and you're a computer scientist, you use 0 and 1 as a binary system. Also very important. So 0 is actually probably the most important integer. And did God create it, or did we think of it afterwards? Kronecker didn't say that. So even with the integers, it's not so obvious. Now, going on with integers, one of the things mathematicians like to do with integers is to factorize them into prime numbers. So the number 6 is 2 times 3. And you can ask, is this a discovery or not? Well, if you have 6 things and you put them in an array, you see they form 2 rows of 3, and that's a nice obvious pattern. So 2 times 3 equals 6. You might say that's a discovery. But the question, and then the numbers which cannot be factorized are called prime numbers. 2, 3, 5, 7, 11, 13. And mathematicians have always liked studying prime numbers. They're beautiful things. They're somehow fundamental numbers for multiplication. And they're still studying prime numbers now. Well, the question is, these prime numbers always existed. If God created integers, somewhere in there were the prime numbers of which all other numbers can be made. But we decided, or mathematicians decided, to study these and define them. God didn't tell us in advance, look for the prime numbers. We thought of it ourselves. Now, many often give the examples of prime numbers, what they call number theory, as the most extreme form of pure mathematics, which is obviously of no practical use whatsoever. Well, if you want to build things out of 2 and 3, it's quite useful to know, but that's not very important. But it turns out in very recent times, prime numbers have been used for a very important application in the modern world, the application to cryptology, how you encode information in a digit form which is secret, how the banks can keep your bank accounts without everybody else finding out how much you've got in the bank or how much you owe the bank. So this is a very recent discovery of a subject which has been studied a long time and was thought to be entirely a pure part of mathematics, and now it's become a very important part. And that actually is a good example of a general principle. It's very hard to distinguish between the parts of mathematical which are useful and the parts which appear not to be useful, because this changes with time. Now, I've talked about geometry and I've talked about numbers. Let's go mix the two together. And the first questions which arise are problems like this. If you have a square with sides of length 1, then by Pythagoras' theorem you work out that the diagonal of the square is the length, the square root of 2. And this, of course, was known to the Greeks, and it's a great problem because the square root of 2 doesn't exist as a number that you can write down in simple form. It cannot be written as a fraction, p over q, and a little box over here, if you like, gives you a very quick proof that you cannot do it like that. So, but on the other hand, geometrically, it obviously exists. The line can be drawn, and it's there. And so the question is, the relationship between geometry and numbers is not so simple. And this worried the Greeks for a long time, and mathematicians for a long time. And eventually, mathematicians invented a way of writing numbers down which are not finite fractions, but involve things like infinite decimals. So, for example, the square root of 2, you can write down as 1.414, and you keep going forever and ever, ever. This is a very complicated notion that you go on to infinity. Infinity is not an easy notion. So, was this a discovery that you can write numbers down in this infinite way, or was it always the case? Because after all, the square root of 2 was lying around every time you measured a square. Not so easy. Let's go something going beyond integers. Let us consider negative numbers. If you have the numbers 1, 2, 3 marked out on a line, and you put down 0 where you start, then if you want to go to the left of the line, you have to think of some numbers, call those, and you call those -1, -2, -3. In other words, you can distinguish between going forwards and going backwards, or going up and going down. Or if you're in the financial world, you're either in the red or you're in the black, the balance sheet. Very important. So these negative numbers, of course, are very important things. And when you have numbers, you can multiply them, as we multiplied numbers before. But if you have negative numbers and you multiply them together, then you find the rules require you that -1 times -1 is +1. That's because if you think of -1 as turning around and going backwards, and you do it a second time, then you find you're going forwards again. You try it with a car. Do a U-turn and another U-turn. So this is an important rule of elementary arithmetic. Now, what's going on here really is that the numbers are things you start off, if you like, by you meet them in practice, you experience them, but then you organize them and you invent a notation to handle them. So there's a combination of discovery and invention, even in elementary things like numbers. Now let me move on to something slightly more complicated, and it follows immediately from the formula that -1 times -1 is +1. That's to do with what are called imaginary numbers. If you take the equation x squared equals -1, and you look for a number which multiplied by itself is -1, you find it does not exist. If you take a positive number and the positive number is positive, if you take a negative number and the negative number is still positive. So no way can you get a number which multiplied by itself becomes negative. It does not exist. That was the standard view of mathematicians, of course, for hundreds of years. Imaginary number, a number which satisfied this equation, was called imaginary. It did not exist. But nevertheless, it was found to be useful. It does not exist in the physical world. There's no such thing as an imaginary number. But if you pretend that it exists, you use it for formulas, you find it's quite a useful tool. And since mathematicians sometimes like things which can be used for applications of some kind, they gradually got used to the idea that maybe imaginary numbers should be allowed. And nowadays, they are useful not only in mathematical formulas, they are fundamental if you're an electrical engineer, for example. Oscillating phases are all described in terms of imaginary numbers. If you're doing quantum mechanics is all based on complex numbers, which are combinations of real numbers and imaginary numbers. So complex numbers, which involve imaginary numbers, are things which clearly do not exist in any obvious sense. The notion imaginary really is indicating that it does not exist. Yet, it's turned out to be so useful, and you find applications and interpretations for it, that it does relate to things which do exist. So the question of the relationship between existence and invention and existence in another form are very subtle. Complex numbers are also, in a way, hidden inside special relativity. Now, I think if you ever ask a mathematician, what is the greatest single achievement in mathematics in the history of mankind, I think it has to be the invention of imaginary numbers. It's a fantastic leap of the imagination to say that this does not exist, but nevertheless we will use it and we'll get useful results out of it and we'll give it a name, and it becomes absorbed. And after 300 years, everybody in the elementary classes in university does imaginary numbers without thinking about it at all. But the great mathematician Gauss, who was the first person to really understand how to treat imaginary numbers in a proper mathematical way, he said the true metaphysics of the square root of -1 is not simple. Because you think you understand it, don't be misled. Now let me move on to some other aspects of mathematics which involve slightly different ideas. That's to do with universal constants. We all know the importance of the number pi, which is the ratio of the circumference to the diameter of a circle. This has been known since the days of Archimedes, and this number is not a number which you can write down as a fraction. It's a number which can be written down as an infinitesimal. And it's a very difficult number to write down. It's a very difficult formula to compute. And of course, Archimedes computed it by taking a circle, drawing inside it a polygon with a large number of sides, measuring the length of the polygon, and as he drew polygons with more and more sides, the length increased gradually, and in the limiting situation, when you have infinitely many sides, so to speak, then you get the circle. So you can get as close as you like to the length of a circle, circumference of a circle, by drawing more and more carefully smaller sided polygons. Now, of course, the pi is a fundamental object in mathematics, not just because it answers a geometrical problem, but because all phenomena which are periodic in nature, where things repeat, the Earth goes around the sun, your hands go around your clock, everything goes cyclical. Every cyclical motion is based on the circle. The circle is the abstract notion of going around. The word cyclic is related to the circle. So it is fundamental in the whole of mathematical theory And understanding pi was not a little exercise of geometers, but it was a fundamental step forward in the development of science. Another fundamental notion is the number e. E is not so well known in the general public as pi, otherwise we would have a Greek letter, but it has only English or Latin letter. E is number also infinite decimal, 2.718, etc., etc. And this is fundamental to understand things like exponential growth, population growth, for example, or if you're more commercially minded, compound interest. There's the formula that I've written down here, which tells you how to calculate interest you get from the bank. If you go to the bank and you're a friendly bank manager, and the bank manager says, I'll pay you 100% interest. It's a very, very friendly bank manager. In some countries, it sometimes happens for a short period. So you give him £1 at the end of the year, he will say, here, you've got £2 now. That's fine. But suppose he says, I'll be even more generous, I'll pay you interest every month. So then when you pay interest every month, you get compound interest and you get more than £2. How much do you get? Well, what you get is this formula here, 1 plus 1 over 12 to the power 12. And that gets more than 2. And if you pay not every month, but every day, you take n to be 365. And if every second, it gets bigger and bigger. Well, if you do that with arbitrarily large numbers, you'll get to the number e. E is the number you get to when you have a very friendly bank manager who pays you every single second of the time. But of course, it has more important applications than that. So the exponential number, pi, are two of the most important numbers in the whole of mathematics, the whole of science. They govern cyclic behavior, and they correspond to exponential growth. And people have always said that if we communicate with life on other planets, if NASA sends out a rocket into space, and eventually this reaches some distant civilization, we want to convey a message to tell them how clever we are. Well, it's no use sending them a bit in English language or Spanish. They may have totally different ways of communication. But if they're intelligent beings, they will have worked out some mathematics. At least we think so. And so important numbers in mathematics, like pi and e, which represent fundamental things, they will know them. So somehow or other, you have to send us something out into space that tells them we know what pi and e are. Are you as clever as we are? Other people say they should not only send mathematical constants out, they should send physical constants out, things which are fundamental in physics. For example, the ratio of the mass of the proton to the mass of the electron. These are physical constants, and if you're studying physics, you have to find these numbers somehow. You will know where you're doing. And how about sending them a picture of the icosahedron? A very beautiful object, very difficult to find, and maybe far out in outer space, somebody also has found an icosahedron. They will see at once that they're doing the same thing. So those are ways of indicating how important these notions are. They transcend language, they transcend barriers, they even transcend perhaps the planet we live on. Now, one of the most remarkable formulae in the whole mathematics is the formula that links together these important numbers I mentioned, e, pi, and I, the square root of -1. And this formula here is in this little blue box that says e to the power pi I, and the e to the power x is given by the infinite series on the previous transparency, is equal to -1. This is such a beautiful formula. I like to tell people who don't know mathematics, is that what is the most beautiful piece of writing in the English language? And if you think about it, many people might say it's Hamlet's, the quotation from Shakespeare's Hamlet, to be or not to be. Because that is a one which has extremely simple words in it, yet it has very deep philosophical meaning. And this is a similar thing. It has the basic ingredients are the most fundamental building things in mathematics, e, pi, and r, and they encapsulate it in a formula of exceptional elegance and deep meaning. Of course, the deep meaning, you have to dig and find out what it means, like you have to dig and find out what this means. And it has you have the right point of view to understand complex numbers and the complex plane and the circles. Then you understand what the meaning of this formula is, and it is fundamental in mathematics and physics applications. It is, I say, if I was the greatest discovery or invention in human history, in mathematics, this formula here is the most single beautiful formula in the whole of mathematics. And I now mentioned beauty, and I mentioned beauty at the beginning, and I said that beauty plays an important role in mathematics. And perhaps I can digress a bit to say why this is true. Mathematicians, like myself, we do mathematics because we enjoy doing it. We know it's useful, and sometimes Some bits are more useful than others, but why do we do it? Well, we do it because we're driven, we enjoy doing mathematics, and we get satisfaction doing it like an artist does. If you paint, an artist paints a picture, he doesn't paint it to put it in a museum or to sell it on the market. He paints it because he likes painting, and he gets satisfaction from doing a beautiful painting. Or if you're Beethoven, you compose a piece of music because you like the beautiful sound you make. There's a beauty in it. And similarly, mathematicians are driven by looking for beautiful results, a beautiful formula, beautiful figure, beautiful argument. And beauty is a very important driving force. It's the thing that makes the mathematician look and achieve the objective he wants. He looks for nice, simple things which have some deep meaning. And in some ways, when you think about it, the whole of science is about that. Science is trying to understand the complicated world we live in by some simple elementary truths, which you can help to explain the whole complexity of life, one way or the other. So simplicity, which is very closely related to beauty, is the essential thing that guides scientists. If you have a lot of possible answers to a problem, you choose the one which is most elegant, simple, and economical. Why? Because our brains are so built that we appreciate that kind of thing. And I'll come back to that more later. But beauty is an important part of the process of thinking, whether in mathematics or in science. Now let me go back to geometry. Geometry traditionally is associated with origins with Euclidean geometry. And Kant, the great German philosopher, spent a lot of time thinking about the nature of geometry. To what extent is geometrical thinking experienced in the outside world, and to what extent do we invent geometry in our midst? And it's a very carefully balanced argument. It's not so straightforward, but he pondered deeply on the meaning of geometry. Is it an experience, or is it something we invent? Well, to some extent this question was settled by advances not in philosophy, but in mathematics. In the 19th century, a great discovery was made that there are things called non-Euclidean geometries. In the old days, Euclid's geometry laid down some axioms, and in particular there was the famous parallel postulate axiom that says through every point in the plane, every line, you can draw a line parallel to the first line, a line that does not meet it. And if you assume this, then the rules of Euclidean geometry follow, and you find formulas, for example, like the angles of a triangle add up to 180 degrees, or pi. But in the 19th century, it was discovered by many people, Bolyai and Lobachevsky in particular, that you can work out geometry which did not satisfy the parallel axiom, but satisfied all other axioms, and in these geometries, the angles of a triangle do not add up to 180 degrees. They can either be more, or they can be less. And this was a shattering sort of discovery in a way, because it showed that the relationship between geometrical thinking in the brain and physical experience outside is not simply a correspondence which is unique. There's no unique solution. There's no unique, we don't know. Well, the question is, what is the outside world? Is it really flat, or is it curved in some way? That is, in principle, an experimental fact. Before that time, they thought the world was flat, therefore, and it could be that the human mind was built on sort of flat principles, and the two things corresponded. This really separated out, it freed mathematicians from having to think that their world was based on the exact world. It could be other worlds which did not exist, but you could imagine them. So mathematicians were freed to pursue their thoughts without always trying to see whether they actually corresponded to the exact world you're living in. Then they invented new things. And of course, the irony was that they went off and invented these new things, and years later, Einstein discovered that these curved geometries did in fact correspond to the world we live in, and correspond explained gravitation, and Einstein's theory of gravitation was born. It wouldn't have happened if people hadn't imagined in the first place that things could be otherwise, that things need not be flat. So you have to use your imagination to get away from the things you've got from the past, which you think have to be so. You can imagine other worlds which are quite different in all sorts of ways, and perhaps one day they will have applications in the real world, like imaginary numbers, like non-Euclidean geometry. Well, the famous relationship between geometry and physics, or mathematics and physics in general, has been so intimate. So much physics can be formulated in mathematical terms, equations simple equations like Newton's equations, Einstein's equations, Maxwell's equations. These are simple equations that explain a vast amount of phenomena in the physical world. And so Eugene Wigner, famous physicist, he referred to this as the unreasonable effectiveness of mathematics and physics. What he meant was this, that, okay, you can explain why some bits of mathematics are useful in physics because you develop the mathematics in order to study that bit of physics. They could go hand in hand. Once you've done that, you find that the mathematics that you've got turned out to be useful far beyond the limited range which you originally started. So mathematics in the early days was about the physics of the time, physics of ordinary sizes we live in, the human scale. But then physicists started to explore things down to the atomic scale, or subatomic scale, or the astronomical scale. And they found the same kind of mathematics worked at these enormous scale differences. That's what surprised Wigner. Why was it the mathematics which we developed in order to understand things at the human scale were also valid at these either enormously large or enormously small scales? That he regarded as mysterious. Why? Well, God created the universe according to these rules, and there we are. Or you might believe in Plato in the existence of an ideal world. Or you might believe in Darwin's theories of evolution, that our brains evolved in order to understand the physical world, therefore they have to reflect the physical world pretty accurately, otherwise we would not be here to discuss it. But of course we don't live at the microscopic scale, nor do we live at the cosmological scale, so that really doesn't deal with the question of why mathematics is useful at all sizes and all scales. Now this quotation of Wigner's, I've recently like to use it in reverse, because in recent years the interaction between mathematics and physics has turned out to be so remarkably fruitful, but in the opposite direction. Not only have physicists found mathematics a marvelous tool to explore physics, but it turns out that mathematicians have discovered that some of the things that physicists do in turn had a profound effect in mathematics in a very, very surprising way, not just in the way of giving you further insight into the kind of mathematics you used before to study physics, but giving you insight into the kind of mathematics which seem very far removed from physics. Some bits of mathematics which were regarded as so pure and abstract, they had no relation to the physical world, suddenly physics gives you some tools, some techniques, some ideas, some concepts which suddenly enlighten a whole area. This has happened in a very remarkable way over the last 20 or 30 years, and I spent much of my time in that period talking with physicists and being so impressed with what comes out of it. So I turned Wigner's question round. I refer to the unreasonable effectiveness of physics and mathematics. I think it's much more unreasonable. Why should the outside world affect our internal world of mathematics in an equally surprising way? Now, having turned to geometry and the relationship with physics, I now want to, if you like, move up a gear and bring you up more to the frontiers of present-day thought, because these philosophical questions I've raised, of course, people say, well, they're interesting questions to Plato and Kant, but they don't really help modern science. They're outdated, old-fashioned, and we scientists know much more now than Kant and Plato and so on. Well, that may be true, but the way things are going, things look more complicated again. Let's go into the question of higher dimensional geometry. Geometry on the line is the geometry of one dimension. In the plane is the geometry of two dimensions. In the plane you can have two-dimensional things can be curved. You can form surfaces. You can be in three-dimensional space, which is about volumes and things like this. Or you can be, in Einstein, if you incorporate time as the fourth dimension, you can be four-dimensional space-time, which is the standard space on which physicists work. But what about dimensions more? Why stop at four? Mathematicians can imagine dealing with 5 dimensions, 6 dimensions, because you simply give a point in 3 dimensions, you give 3 coordinates, x, y, z. Well, you want another coordinate t, you get x, y, z, t, but the alphabet doesn't stop. Your mathematicians can invent more letters. So you keep adding dimensions, and you can write down equations in many more variables. Mathematically, all dimensions are, in some sense, equally good. But if you think about them in a kind of physical sense, they seem to be really outside the world we live in. And when mathematicians in the 19th century started seriously to work with more than 3 dimensions, people wondered what they were doing. And in fact, the famous British mathematician Sylvester, who was, I should say, besides being a mathematician, he was a great linguist. He spoke many languages. He was a poet. he gave his inaugural address at Oxford University in Greek verse. He was a very cultured man, and he wanted to give a word to this use of higher dimensions. He suggested they should be called inconceivable. Inconceivable. You cannot conceive of them. You cannot imagine them. It's like the same idea of imaginary numbers, but imaginary numbers had been used. He wanted another word. And, well, the word didn't catch on. But if he had caught on, we would be referring to inconceivable dimensions. But things move faster, and now we've used the higher dimensions without waiting for the terminology. Now, one of the surprising things of the last 10, 20 years, 30 years, is that modern physics now postulates there are, in fact, more than 4 dimensions. There are more than 4 dimensions, and you can write 10 dimensions. For example, 10 dimensions is a very popular dimension for reasons which are technical, which I won't go into. And these 10 dimensions can be thought of as the 4 dimensions of space-time plus 6 extra dimensions. Or sometimes you go into 11, then you have 4 plus 7. And the idea to explain what this is about is something like this. You think of the other dimensions besides the 4 as very, very small, only sort of ultra-microscopic scale, and very tightly curved, like very, very small circles. So a very, very small circle doesn't look much different from a point. You don't notice the extra dimensions unless you get a very big magnifying glass. A big magnifying glass for a physicist is something like an accelerator, a big machine. So if you live away from these big machines, you don't see these extra dimensions. You live your ordinary life. We move in space and time. But for the physicists, they postulate there are these other very, very small dimensions which they see in their big laboratories in CERN, where they bombard particles. They see phenomena which seem to indicate there are other dimensions beyond the 4. That is a very big step forward in concepts and challenges, and the question is, do these extra dimensions really exist? So far, these are somewhat theoretical concepts, but there is what you might call very indirect evidence for extra dimensions. If you suppose these extra dimensions exist, then you can build theoretical models which are consistent with experiment to a great extent. So you suppose these don't exist, you write down formulas, and the formulas lead to experimental results which you check, and they agree with theory to some extent, so you have a test of your theory. But you never see the dimensions in any kind of concrete way. They are fictions of the mathematical imagination. And so the question is, are they real? And what does reality mean? Well, here we get back really to the philosophical questions of 2,000 years ago, or questions which concerned Immanuel Kant. And what is reality? What does it mean for something to be real? You do experiments, you test numbers, you write down formulas, but is that what reality is about? And this becomes even more significant when sometimes the physicist will tell you, well, I can interpret these extra dimensions one way, but I can interpret them another way, and I will get the same answers. So there's no necessarily unique picture of these extra dimensions. Then the question of are they real becomes even more mysterious. How can they be real at the same time in 2 different ways? Reality is, if it exists in a naive sense, is one thing. Can you have 2 different realities? So the question about the relationship of mathematical models, which is what they are, and reality becomes a very, very pertinent question in the present day when people are dealing with complicated theories to explain extremely small quantities or extremely high energies or the nature of the universe or black holes. All these very elaborate notions involve the possibility of extra dimensions which are lurking in the background, which we never see, but whose consequences we can sometimes help to understand. And now this question of the relationship of reality to physical world is also a question of supposing there were alien minds outside in other forms of the universe, would they invent the same mathematical models to explain the physical world which we commonly live in? Or are there different possible alternatives for the pictures that you produce? Now at this point, I think we find that, you see, when you ask these questions, you are dealing both with mathematics, with philosophy, and with physics, and interpretation. But at the end of the day, all of this thinking takes place inside the human brain. The human brain is where ideas live, really. Your human brain and my brain, that's where where we think. And nothing outside the brain really exists for us, in a sense. Everything is filtered through the human brain. So, in some sense, mathematics is created by the human brain. The human brain is the piece of machinery that produces ideas, and mathematics is a form of ideas. So the brain has created, and not just a brain, but the collective brain of mankind over the centuries, has created mathematical theories. They are output of the human brain. Now, the human brain is the product of evolution. It's arisen out of millions of years of development in the biological kingdom, and evolution is, of course, works by natural selection, and so the kind of it's based on physics and biochemistry and so on, and the ultimate output of the human brain has to somehow be consistent with the physical world outside, otherwise we would, as I said before, we would not have survived. So the fact that we are here means that our human brain has, in some sense, to reflect the physical world outside. For example, even the notions of things like cause and effect. If you think about it, all science is based on the idea everything that happens has a reason, cause. Cause and effect are, well, we didn't have that, we wouldn't know how to act. So cause and effect are reflected in mathematical thinking by the notion of a logical implication. This implies that. Given this one, you can deduce that one. That's the logical analogue of the practical notion of a cause producing an effect. And without living in the outside world and experiencing it, we wouldn't have abstracted that notion. So the human brain has evolved from the outside world, and mathematics is part of that creation, and is part of the process of abstraction. Mathematics insists in looking at the outside world, finding many common features in different situations, finding a single formula, single idea that unifies it, and then developing that in detail, and then applying it back into the real world. That's what mathematics is about. It's about abstraction, finding common features. Many things, you count 2 apples and 2 oranges, they're both 2. You go back to the real world and you buy 2 bananas. So abstraction is fundamental to mathematics. And in some sense, it's probably the case that abstraction is a fundamental process in brain structure. We don't know how we think. One of the questions which neurophysiologists are now trying to understand is how do we think? What is the nature of thought? What is the physiological nature of thought? What happens in the brain when an idea is conceived of and then used? Now, this is beginning to be a question that you could address. Neuroscience has now reached the stage where you can begin to ask sensible questions, the kind of questions that philosophers in the past asked, but they could never answer. Now, neuroscientists can begin to answer the questions because you can take a volunteer. Anybody in the audience want to volunteer? I'll put you into a machine, and now we don't need to cut you open. They can just scan you and find out which part of the brain lights up when you ask the question yes or no. So you can identify, in rather precise ways, the parts of the brain that are involved in various sorts of mental processes. And you do this carefully, you can actually answer certain questions. For example, one of the questions you begin to answer is, to what extent is the brain hardwired to do mathematics? Okay? Are we born with somehow fundamental ability to do mathematics, like we are born with some fundamental ability to talk languages, not English or Spanish particularly, but the ability to talk the language that is in front of us when we grow up. That's undoubtedly hardwired in the brain. We have a capability to do that, which has evolved through evolution. And to some extent, something similar must be happening in mathematics. We have some mathematical notions about how to do elementary arithmetic, which are probably hardwired in the brain. That you can begin to test out. You can find out which parts of the brain are involved, to what extent the various mental processes can be identified. So you can begin to answer the question, is mathematics in the brain, or was it outside? Well, if you end up by saying it's in the brain because you find out the neurons that work, then you can say it's inside the brain. But on the hand, neurons and so on are built ultimately of physical objects, which are part of the outside world. So the distinction between the brain, the inside brain, and the outside world is not as straightforward as it seems. So let me try and finish with this sort of little diagram. The question the philosophers worried about in the past was the nature of mind and matter. what is the brain, to what extent are these material things, to what extent are these abstract ideas. And this is reflected in the sort of thing I've been talking about here, about the relationship between mathematics and physics. Mathematics is concerned with ideas which live in the mind. Physics is concerned with the phenomena dealing with the real world, which correspond to matter. And these all take place, of course, inside the human brain, the interaction between them. So the level which philosophers think and the level which scientists think intersect in this way. And the more we understand about the workings of the human brain, the more we can clarify the relationship between mind and matter and the relationship between mathematics and physics. So what is I asked the question at the beginning, do we invent or do we discover things? Well, as I said, that kind of question doesn't really have an answer, yes or no. But you can try to give some sort of answer. So you can say in the real or Platonic world, either the actual world outside or the world of ideas, there are millions of possibilities. Lots and lots of things are possible. And what the human mind does is to select a small number which it regards as interesting. You know, it's said that if you give a monkey infinite time and a typewriter, one day it'll type out the entire works of Shakespeare. Mathematically, it takes millions of years, but eventually he'll get there by just chance. Well, we are more of a hurry. We don't wait millions of years. We select out things, and Shakespeare writes it first before the monkey. So the human mind selects the words of, once you've thought of letters and symbols, you can put them together in words mechanically. A computer can just juggle them together. There's no limit to the number of words you can write down, or to the number of sentences you can write down. And nowadays you see that filling libraries, no limit to the number of words you can put in a library. But the important ones, are the ones which we want to select out, are what we do. We select. So selection is a very important process. We choose from the myriads of possibilities the ones which we think of as interesting. But then that begs the question, what is interesting? Why do we do it? That's when it comes down to human judgment. And there the criterion you use become important. So when I said that the important things was choose things which appeal to you on grounds of simplicity, elegance, and beauty, those are the criteria which we use to select the things that we want to concentrate on. We don't just put all the facts in, turn a big handle and say, here is all the data, here's all the information. We try to organize it, put it together, and single out things and select. So the human mind does a process of selection, but you mustn't underestimate the significance of selection. And just as a monkey with a typewriter could write the whole words of Shakespeare, given some mathematical symbols, x and y's, a computer could generate millions and millions of formulae. But a mathematician tries to choose those equations which he thinks of as especially interesting, and he has to have criteria to choose those equations. And that's why beauty is important to a mathematician. It guides him in selecting which ones to study. And this is therefore a human activity, and I would like to emphasize that mathematicians are human beings. We're not computers. We're not machines. And mathematics is a product of human activity over millennia, over centuries. It's there because if you learn a formula in school, you think of it as some kind of dull formula that you're taught by a teacher. It's somehow automatically built in. But somebody had to think of that first. Some mathematician, some human being, had to think of the ideas, develop the ideas, try to write it down, find out the results. A long process of discovery or invention. And that is what part of our present-day culture. So our culture is the accumulation of human activities over the previous centuries. And that applies in mathematics, in science, and in art. All of these are human activities, and we're not just machines which try to generate things in a mechanical way. So I think that's since I began by talking about the similarities between mathematics and science and art, I thought I want to end up with the same point of view. All these things, all these endeavors are human activities, and they are guided by, in some sense, the same fundamental principle, the search for simplicity, the search for beauty, which guides us through the multiple choices that we could face, choose us the right answer. And that is the only way we can proceed. If we generated too much information without structure, without beauty, without elegance, the walls would be filled with a lot of junk. You wouldn't have beautiful pictures on the wall, you just have scribbles and simple formulae and so on. So selection and identifying the important things are what we're here to do. So choose the right problems, get the right answers, and you made your contribution to science or mathematics. Thank you.
Thank you, Sir Michael, for such a magnificent talk. It is really, it has been really a very deep reflection, and I think it is time to open the discussions. Se alguén quere preguntar, que levante a man. Aí apareceu co micrófono. A ver, alguén? Mans arriba. They are very shy.
Yes, okay.
Yes. Okay.
Usted ha hablado de un artículo que se traducía en español como la irrazonable efectividad de las matemáticas en la física. Y ha salido un segundo trabajo que habla de la efectividad de las matemáticas en la biología, sobre todo en el estudio del genoma. ¿Sabe usted algo de... ¿Cree que hay posibilidades de que las matemáticas lleguen al final a interpretar el genoma humano?
This machine isn't working. Can you translate for me?
I thought somebody was translating.
Well, no, the person is probably translating, but the machine doesn't work here.
Oh, yes, I was talking to somebody. I didn't hear the question.
Oh.
¿Pode desarrollar a cuestión da traducción dele?
I half understood it, but not...
No, que estaba despistado, básicamente. Ando falando coa xente que das así un medio cuadros. Además, como a pregunta era un pouco larga.
Okay. Hold it. Wait a minute.
Now you hear?
Yeah, I hear now.
Okay.
Okay. Yeah, so the question is, do I think mathematics can be applied to fundamental questions of biology? Well, I think the answer is mathematics is applied in biology in a variety of ways already. The question is, will the applications of mathematics be of the same degree of sophistication and importance in biology as in physics? That's not at all so clear. Physics and biology have very different structure and evolution and so on. And it's not clear. But anyway, of course, biology is in many ways a young subject, and mathematics becomes important when subjects become sufficiently old, when they get sufficiently complicated. So when perhaps biology gets a little bit more elaborate and asks more difficult questions about the human genome and other things, then, or the structure of the brain, then mathematical models may become more and more important. Already they are. People are thinking about, both in terms of the human genome and in terms of the human brain, the ways in which mathematics can be used. But how successful that will be, I think, remains to be seen. I don't want to make any forecasts. It would be rash to predict, but it's a very different story from the connection with physics.
Preguntas? Well, in the meantime, I have a question. Have you ever been tempted to think about God, about the existence of God? Or something similar? I mean, well, as a physicist, you know that, well, Newton's law, you have that the force is inversely proportional to the square of the distance, and this exponent is 2.00000020 zeros, at least today. And so this magnific coincidence, at least, leads me to think about God sometimes. Why not 2.3? Why not 3.35?
I think I think Newton's laws, inverse square law, is I wouldn't think I'm very impressed with. Yeah, right?
Yeah, you can talk about it.
Yeah, so I don't think I'm so impressed with that number 2 in the inverse square law. Some numbers are fundamentally integers, sometimes for lots of good reasons. And if a number has to be an integer and it's 2, it is 2. It isn't 2.003 or 2. If a number could be anything, then it could be some very, very small change from 2. But if a number has to be an integer, then it has to be, you only need to get close. I think that the inverse square law is more of that kind. But you're right, in the other questions, people who study the evolution of the universe will say that if the universe in the Big Bang day wasn't tuned very finely, certain constants being what they are, then it wouldn't have evolved, we wouldn't be here, and therefore God must have made the universe so that we would exist, and he had to be there to get the numbers right. This is certainly a famous argument called the Anthropic Principle. It's an interesting argument, where he tries to bridge the gap between religion and science, if you like, but it's controversial, and at some stage people may say it just describes ignorance, we don't know why. So I'm an agnostic. I'm open-minded, but I don't see any convincing arguments, totally convincing arguments at the moment. You have to be careful not to accept things too much at face value on this kind of argument. But there are some scientists who, of course, believe, well, Stephen Hawking uses the word God very often in his books, but he uses it in a kind of, almost as a kind of joke. Many other mathematicians use God in a kind of fictional way. They said, if God created the universe this way, then we have to follow the rules. But by that they don't mean God in any sort of ordinary dogmatic sense. They simply mean the universe is created, and however it's created, you assign the name God to that. So the word, if mathematics and physics are difficult notions, human mind is a difficult notion, the notion of God is an even more difficult notion.
¿Más preguntas?
Thank you, Professor. I heard a strange question, I suppose. In the elementary school, we have been taught that man made maths, but maths makes man mad. Yeah, but my question is, at what extent we are going to use mathematics in our day-to-day application? Like, there should be some limit for that. Like, we can't avoid using maths, but we need to use maths, but there should be some limitation. So what do you suggest us today? Like in a day-to-day our relation or in our communication, we can apply maths in a different ways, but what do you suggest us? Like, sometimes it makes us mad.
Well, mathematics is used, in everyday life in a wide variety of different ways. Some of it in elementary way, you go to a shop and you buy something. But in many other ways, in a much more sophisticated way, every time you're using, a piece of hi-fi equipment, you're using the laws of physics, which are involved Maxwell's equations, which involve mathematics. So mathematics is at the foundation of your life. Even if you don't know it, you may not like it, but you wouldn't be here you wouldn't have all this machinery and lights and so on. So mathematics is at the basis of modern technological civilization. And different people, of course, you see different parts of it, use different parts of it. And the ordinary person in the streets only sees, of course, a very small part of it. But if he becomes an engineer, he sees more. If he becomes a physicist, he sees more. So mathematics has a depth. Some parts you see on the surface, some parts at the bottom of the ocean. And depending where you live, you see different bits of it. You can't be mad with it. It's your environment. It's tough luck. You like telling a fish, and he doesn't like water,
si podemos relacionar la complejidad de las matemáticas con la capacidad de, o sea, con la cantidad de inteligencia de un ser. O sea, sabemos que los animales tienen su nivel de matemática, saben contar, saben sumar, algunos, según sea.
He has to use the microphone. The translator can't follow.
On the complexity of mathematics, of
Yes.
human mathematics, and the complexity of the human being.
Yes.
So he says that some animals have a certain ability in mathematics, but it's a simple one. So I guess that the question is, the simpler are the mathematics, the simpler is the human being, the animal or the human.
Entonces, viendo cuál es el comportamiento de los animales con respecto a la naturaleza, que son capaces de integrarse en ella, y el ser humano, que es básicamente la tendencia es a destruirla, ¿hasta qué punto las matemáticas tienen que ver en el carácter destructor? O sea,
Sí.
¿Hasta qué punto es una prueba las matemáticas de que somos más inteligentes que el resto o que la inteligencia se trata de una herramienta útil para la naturaleza? Es que es difícil de plantear.
So the question is, does the fact that we can do mathematics show that we are more intelligent than other animals which can't do mathematics? I think, there's not much doubt that mathematics, like language, is only formed at the highest levels in human brain. The human brain is much more complicated than animal brains. Some elementary things can be performed by other species. Elementary bits of arithmetic. You can teach a rat that 2 + 2 = 4. This has been proved experimentally. But you can't get it to prove Pythagoras' theorem. And similarly, animals have various means of communication. And you can teach a chimpanzee small vocabulary of words, or you can teach a parrot some words. But these are very, very limited. And so there's no question that, for obvious physiological reasons, the human brain is so much more complicated than any animal brain by orders of magnitude. It's no surprise that it is capable of much more complex intellectual operations. Mathematics is one, language is another. So I don't think it's really a matter of debate by biologists or philosophers. Of course, it doesn't. You have to be careful not to go too far. It doesn't mean that human beings have a right to do what they like with all other animals. You may have moral arguments that we should preserve other species, and that's a different question. But if you're more intelligent than me, it doesn't entitle you to kill me. I mean, So being more intelligent means you have more responsibilities, if you like. You should be more responsible, do better things, be a better person, look after the planet. So intelligence carries responsibility, shouldn't carry power. And I think there's no real debate amongst people who look at it quite seriously as to whether we are more intelligent than other animals. That's not really an issue. It's obvious both in the level of operations, what you can do, and in the levels of physiology, what your brain consists of. You know the answer there.
You made a previous comment on the fact that humans tend to destruct the planet and animals tend to preserve it. So maybe the mathematical complexity is a danger.
Well, of course, it's true. The intelligence gives you power, gives you ability to do things. And if you don't use that well, then you may get the disastrous consequences. Human beings may entirely obliterate themselves, or may obliterate the world, and may go back into a Stone Age. It's certainly not an impossibility. And we are in some ways quite at a critical stage just now with the global warming and other dangers. So that's certainly true. And if you believed in God, perhaps he shouldn't have created human beings. He just kept us at simple levels. We couldn't damage his beautiful world that he created. So, but that's life. We're here and we have these abilities, and we're propelled along a certain path. It's human choice whether we survive as a species and whether we survive as a planet or not. And nothing much you can do about it, unfortunately. You can't suddenly say, well, we're all going to go back to stupid, we'll go back, not forget what we learned in school, and go back and live in the caves. That's not a practical solution.
Well, a small question about the brain. I was in the 50s. There was the belief that the brain was more or less an automaton, something equivalent to a computer. So there was the dream of artificial intelligence, and I think that the program of artificial intelligence is basically stuck now, even though this apparent success with Deep Blue, it is very fast evaluating chess plays, but not getting inside. And there's a speculation by Roger Penrose about the possibility of quantum mechanical process going on in the brain, and then the brain is something completely different. What do you have any opinion, any feelings about these things?
Well, first of all, I should say Roger Penrose was a colleague of mine, he's a good friend, but I don't necessarily need to agree with him. I think that certainly the case is, in the early days of computer science, and when not so much was known as about the brain, computers said, aha, now we understand how information is processed and handled by the computer. The brain is just a very big computer. That's disappeared now. People, because they realize that the brain does, first of all, the brain does not work just like a computer. It does not work by binary codes and mechanical systems. It's a very much more complicated structure with very much more complicated pathways, which people are now beginning to understand. And it has much more plasticity and variability in ways of learning than, so if you thought of it as a computer, it's a computer of a different order of magnitude from anything we have now. Not just in terms of speed, but in terms of logical complexity. There is a certain fundamental similarity that any machine that processes information, produces an output, has to have some kind of basic semantic or logical structure that has some similarities. But the mechanics of how it operates and the degree and the levels of which it operates can be very different indeed. And the more people learn about the human brain, the more the difference between computers and the brain appears. I think we're getting further away from this simple-minded idea of the past than it was. It's not converging, it's diverging. So, and people are learning much more about the brain now, and the more they learn, the more they realize that it operates in a very different way from ordinary computers. Computer is much faster in certain processes, but is much less adept in other ways. And so, as you know, artificial intelligence can do quite well at very limited processes, like playing chess, or answering particular sets of questions of a very limited kind, where you have no, yes and no choices. But anything involving much more sophisticated reasoning or insight, or there's no begin to deal with those questions. So they've given up on. They haven't got to the point yet where we can replace all our politicians by computers and hope the world will be better. Maybe it'll come. Well, there was seriously a time people thought, well, the world is going, as I said, so dangerous with human beings in charge. We must hand it over to computers who will be much more sensible, and they will organize the world so we don't fight wars and so on. And that will be the way we will save ourselves. That's a kind of science fiction dream.
¿Más preguntas?
Yes, I just wondered if you had any thoughts on human consciousness, because that is where you were leading towards the end of your lecture. Well, anyway, I'll stop.
Yeah. Well, again, human consciousness is one of the, there are a list of big problems which people in neurophysiology are now thinking about. Consciousness is high on that list in some sense. And Roger Penrose, I think, he even has some ideas on that. I am much too modest to even attempt to answer that question. I think consciousness is one of those questions, I think, which is, will disappear. Like, in the old days, you go back 50 years or 100 years, people said, what is life? That question has disappeared now in many ways. You know so much more, and it's not an intelligent question. We know much more about DNA and viruses and so on. We've subdivided the question, analyzed it, and it's disappeared as a question like that. I'm sure that the same thing will happen to consciousness. What is consciousness will disappear because you will first of all discover as you already know, there are many different kinds of consciousness, different levels of consciousness, different degrees of consciousness. It's not a single thing. And so that question, I think, will disappear as we learn more. It won't be answered in a simple way, but we'll just learn more about the whole subject. And at the moment, I think we're just beginning. I think 50 years' time, if I'm here in 50 years' time and you ask me the same question, I might be able to give you an answer. But I don't think we're anywhere near understanding that question, because it's the very hardest question of all, because it has to do with the nature of self and the nature of who you are, and what is the person who is thinking, who is he, and all these questions. So you're right, it's the fundamental philosophical scientific question. But I think, again, the kind of question which philosophers have asked in the past, the nature of I, the nature, and which science will shed a lot of light on. And when it sheds a lot of light, the question will have disappeared, as philosophers put it, and will be replaced by a scientific discourse. So I think it will be a question that will emerge in 50 years, I would say, some better understanding of consciousness will exist. But it won't be a simple yes or no answer.
We had here Thorsten Wiesel 1 month ago. Maybe he could answer your question.
Well, we can ring him up,
I hope I can formulate my question. Recently, there has been many books published by, questioning if string theory would be the right path to do the grand unification. What's your feeling about it?
Well, string theory.
Just one book recently had a really nasty title, like "Not Even Wrong."
Yes, I know. Well,
by the way, you are sit close to a string theorist. So.
There's a gap in between. I mentioned that there are various sophisticated mathematical models of present-day physics involving more dimensions and so on, and the ultimate goal of these is to produce a unified theory that incorporates Einstein's theory of relativity and quantum mechanics, elementary particles, in one big grand theory. That's the ambition. And string theory is, at the moment, the most popular tool with that goal in mind. You'll have different views by different sections of the physics community. Some people think this is all nonsense, mathematical idealism. Others think they're very near to the answer, and I mean, always in between. So I think that the answer is still open. String theory is a very promising program. It's a very interesting mathematical structure, no question. It's very useful in mathematics. Whether it's really the ultimately the right way to look at it, we don't know. It may be that it's very close to the answer. It may be it's a long way to go. Maybe some new young Einstein will come along and say, look, you looked at it all wrong. This is the way you should look at it, and our whole picture is transformed. So at the moment, I don't know. You can toss up which you think. I think you should be careful not to believe too much from anybody. There are people who write books and sell a book. You can't say, well, I'm not too sure. That doesn't sell books. You have to sort of fly the flag, either plus or minus. Either you say this is a marvelous theory about to solve the problems of the universe, or you say it's all rubbish. Either way, you get an audience and you get money. If you go in the middle and give a very carefully balanced argument, you don't sell books. Now, it's a pity this, because, of course, trying to explain science to the public is an important part of the scientific process. You should try to explain to the public. And it's an important part. But the trouble is, once you start, you're dragged along a certain path. To reach an audience, you have to simplify, popularize, take a strong line, and you go along. Before you know where you are, you're a propagandist for a particular point of view. So it's very hard to maintain a balanced description and still keep an audience. That's a difficult task all scientists have. You ask a scientist, you make a discovery in the laboratory, and the journalist rings you up, says, will this cure cancer tomorrow? And you say, well, I'm not quite sure. No, if you're not sure, forget it. It's not a story. So so some scientists say, well, maybe, okay, we'll include it. So there's very great temptation to oversell, and this is very bad, because if you oversell things enough, then you simply you lower the reputation of the whole field. So you have to be careful not to oversell, and you also have to be careful not to be overcritical. You must encourage ideas, not rubbish every idea that comes around. So it's a very difficult question.
From From the mathematical point of view, I'm a mathematician, not a physicist. String theory has been quite good. It has brought lots of interesting problems and subjects. And
Yes.
Independently on going to give the grand unification.
Yes. No, I mean, see, physics raises physical problems. Then people will try to produce mathematical approaches or models to solve those problems. And in the course of that, they will develop a whole range of techniques. And those techniques, as a piece of mathematics, are perfectly good mathematics. Mathematics exists independently whether the physical application is correct or incorrect, as long as the mathematics is correct. So a lot of very good mathematics comes out of the wrong idea in physics. Sometimes it comes back as a useful idea in some other part of physics. But so mathematics benefits, mathematics are like lawyers. They win either way. Either the case is lost or they make money. So we don't care whether the physics, oh no, we care, but even if the physics is wrong and we get some good mathematics out, we win. The poor physicist loses. So it's not fair for them. But for mathematicians, there's no question. But I think the mathematics coming out of string theory is undoubtedly extremely interesting mathematics, will be absorbed in mathematics, and will be part of the mathematics of the coming centuries. And that's happened in the past. Many ideas of physics have given mathematical ideas, even if the physics finally goes a different direction. Well, that's okay, you experiment.
Sí, hacía usted alusión acertadamente a la importancia que tiene los sistemas de representación, como por ejemplo la invención de los números arábigos para representarlos, posiblemente sin lo cual pues cosas tan importantes como la infinitud de los números o el cero no serían seguramente inventados. O podemos hablar de los sistemas de representación de funciones en coordenadas, etc. ¿Hasta qué punto es importante encontrar lenguajes, sistemas de representación para que determinadas ideas se puedan crear, desenvolver, inventar, etc.?
Yeah, so the question really is the relationship between ideas and sort of representations of those ideas in mathematical, symbolic form. I mean, that's quite correct to point that out. I mean, there are concepts, ideas, then there are sort of formulations of those in some more tangible way that you can manipulate them. They'll be words, they can be formulas, and this is an essential part. As I mentioned, when you have numbers, the decimal notation was a very important step forward because it helped progress the field, and that's a simple example of which many more complicated examples exist. So that applies in something not only in mathematics but even in other fields. So what you have to do really is to take a concept or an idea and make it precise. Precision, it takes many forms. One form of precision is mathematical precision. You take ideas, you write them in terms of formula equations, then they have very precise meaning. But you can have precision which is not necessarily mathematical, it could be still verbal, but clarifying ideas by giving them precision is an essential part of the process, because an idea which is vague remains vague. It doesn't get you anywhere. You have to progress it down the line. And that process is a very important part of the process. You have two parts, the vague, general, creative idea, the inspiration, then the carrying it out of it in a more precise form. And the same thing happens if you're a painter. You may have a great vision of what you want to paint, but eventually you have to get your paintbrush out and do some actual hard work to convey that vision in a concrete form. So I think all forms of intellectual activity have the idea, the concept, and then they have the passage through technique and implementation, representation, eventually to the outputs. And so you're quite right, that's a very important part of the process. You see it in mathematics, but it's not only in mathematics.
¿Más preguntas? Who is your favorite mathematician in history?
Oh,
Favorite.
well, I didn't meet them all. Well, I mean, I came from Cambridge. I have to say that Isaac Newton was, he's a big figure. I also admire Clerk Maxwell as a great physicist. Amongst more mathematicians in recent times, the great Hermann Weyl was a mathematician very much in this kind of mathematics that I like to do. He did a bit of physics, but he did a lot of mathematics. He was very much a man of ideas, and his ideas, you can measure these. I just mentioned, people may not know who he was, but he was a famous German mathematician, died in 1955. He went to America when the Nazis took over. But he wrote in a very beautiful, clear language as well as doing great things. And so he's a kind of hero of mine in many ways. He did many things. And I had an experience recently. Academies quite often write biographies, obituaries of their famous scientists when they die. So I've had to write obituaries of various people. But I was asked by the US National Academy of Sciences to write the obituary of Hermann Weyl 50 years after he died. Nobody had done it. So I took the unusual case of writing the obituary, which was not an obituary about exactly what he did, because so far back, I gave an obituary explaining how his ideas had developed over 50 years after he died. In a way, that's a good measure of the importance of what you do. What's happened to your ideas 50 years after you've died? And it was remarkable to the extent to which his ideas percolate down right to the present time. And so in that way, measuring your impact on subsequent generations.
About Abel, he wrote a book named Symmetry.
Yes.
Do you mean symmetry is beauty, something linked with group theory, with algebraic structures?
Yeah, Hermann Weyl wrote a small popular book called Symmetry, which he for the general public really, he was trying to explain symmetry has to do, left and right are symmetric, symmetries of fundamental shapes. There are more beautiful symmetries, the symmetries of the Platonic solids I described. They are things that look the same from many points of view, and they are part of many aspects of beauty are related to symmetry. Symmetry is certainly a component of beauty. If things are very asymmetrical, they tend to be ugly. So, and what he was writing about was symmetry in mathematics, which has a particular fact. Defining what symmetry means in mathematical terms is a difficult idea, which took mathematicians a long time. Now we have a whole theory of symmetry, which is group theory and so on. So he explained that. It also appears important in physics. Symmetry is a very fundamental notion, elementary particle physics. Particles come in sort of symmetrical combinations. But he also explained, of course, his role in art, taking examples of famous paintings and so on. And also in biology, he took beautiful pictures of primitive animals in the sea, which are, have marvelous symmetrical features. I mean, you see these archaeological or fossils or things. So in nature, symmetry has also been used extensively, and we recognize it there. So it's prevalent right across the spectrum, and it's one of the unifying themes in a way that is common to mathematics, biology, art, so on, all kinds. And he wrote that book as a popular book to express this idea.
Bom dia. A mí gustaríame preguntarle, pido disculpas por si a pregunta non é oportuna, que cree que compañía necesita ciencia, investigación en matemáticas, a investigación en xeral, para facer deste mundo algo máis habitable para todos? Ou preguntar tamén se considera que esa aspiración non é unha aspiración razonable para a ciencia. E preguntar tamén, en caso de que esas compañías para a inteligencia sean necesarias, en que medida as grandes cabezas e os grandes investigadores deben de comprometerse na súa búsqueda. Moitas gracias.
So the question is whether mathematics and science can be put to better use for the improvement of the world, and whether scientists themselves should be pursuing this aim. As I pointed out before, the development of science by itself is a search for knowledge. In principle, the more you know, the more you should be able to do. Whether you do it for good or for bad is then a human judgment which human society makes. The mathematician or the scientist contributes his share of this as a scientist. As a citizen, he has to be involved in the citizen's process to assist the outcome. But as a scientist, he can't dictate the outcome. He can't say, I'm a scientist, I made this thing, you must do this with it. That's not within his power in a democratic world. But he can take part in organizations. I took part in this pugwash movement against nuclear weapons because I thought it was an important thing to do. And that those pugwash conferences, I should say, were founded just after the war by many of the leading physicists who worked on the atomic bomb project. They worked on that project during the war, but they were horrified with the outcome, and then they spent their time trying to find ways to make sure that these bombs would not be used again. And that was the origin of... So that was an example of the scientists going outside, having made their scientific discoveries and realizing the ways in which they could be put to bad use, trying to form organizations which would lobby politically to try to achieve those ends. And to some extent they were successful. I mean, not the only reason, but they were successful in trying to reduce the armaments race and so on. So yes, scientists can contribute, but I think there's more... I mean, the scientists have to be driven fundamentally by their curiosity. You ask a question that you think is interesting. You may also be driven by trying to find something which, in principle, is going to be useful for the world at large. You may have a particular goal in mind, in which case you're an applied scientist. If you want to find ways of getting rid of the carbon dioxide in the atmosphere and bury it in the ocean, that's a technical, logical problem which you may want to study, and that's fine. So there are many explicit problems where you can directly benefit mankind, and many scientists do that, and they could include mathematicians. But fundamental science is concerned with advancing the frontier of knowledge forward, and that is driven by internal curiosity. If you locus too much on the immediate applications, you never make the big leaps forward. I mean, if you think back in the early parts of civilization, when people were trying to transport things, the first person to invent a wheel made a big discovery. Before that, they had different ways of moving things around, and you keep improving the technology. But until you had a new idea, you made only limited progress. So all science has that phenomenal feature that the big ideas come not by trying to solve the immediate problem of the present, by thinking very generally, and then you find things which take you much further forward. So you have to distinguish between what scientists can contribute in terms of the immediate present, which is important, but also making fundamental contributions which are of long-term benefit to society as a whole. And those are very different parts of the scientific endeavor.
Please, could you give us an idea of the main paradigms that we have today in mathematics, in physics? What are the main ideas or the main worries for you for trying to discover in mathematics nowadays? So.
Well, first of all, mathematics is a vast enterprise. It covers an enormous range of different ideas, techniques, partly because in principle mathematics can be applied to so many different things. So there's an enormous range of mathematics, and it's always best to let individual mathematicians pursue their own line. You don't know where the next breakthrough will come from. Sometimes it comes from trying to solve a problem from the past, sometimes it comes from creating a new idea for the future, and it's very difficult and not desirable to try to organize this. If you constrain it, you kill the process. So it has to be a free process of ideas, and at any given moment every mathematician will have his own field of interest, his own ideas he works on. I happen to be interested in the interaction between geometry and physics. I think it's a very exciting area. Many exciting things have been happening in the last 30 years, and I think trying to understand that and the implications for both physics and mathematics, would certainly be a very worthwhile enterprise, and will throw up a lot of new things. But of course, the other parts of mathematics, which I do not work in, which also have great potential, and everybody should be exploring all these things. So you mustn't think of mathematics as a single thing with a single goal. It has more goals than many sciences, because many sciences are focused on a central problem at a given time. Fundamental physics is concerned with particles or cosmology, or biology was concerned with DNA. I mean, they tend to focus on the precise, exciting developments at that moment, the big questions. Mathematics, in principle, isn't constrained that way. You can write it all sorts of ways. So in principle, it's much broader. It covers physics, biology, chemistry, computer science, economics. And so in a way, it has the least constraint, because it's not constrained by the possible reality now. It's constrained by the human imagination for the future, and that's open-ended.
What do you think about the program of Hilbert?
Well, Hilbert was this famous mathematician in 1900 who, at the time, he was invited to give an international lecture at the international conference, and he focused his talk on the 20 or 24 what he thought outstanding problems of the time, and that made quite a big splash, because he was a great mathematician. The problems he picked out, some were well known, some were the ones he focused on, And they made a list that people could then tick off in subsequent years, and many problems were ticked off very quickly. Some proved difficult, some proved impossible. It's a useful exercise, but people in the year 2000 thought they would repeat it. You can't, it didn't work. So producing a list of problems in any given moment is a useful exercise, perhaps, for an individual. And problems are an important part of mathematics. I mean, if you could pose a problem well and leave it unsolved for a long time, it's a great challenge to mathematicians. And a challenge is what produces new techniques and new solutions. So problems have it's like mountains. You climb a mountain, you have to develop new technology to get up with pickaxes, ice axes, and ropes and so on. Then you can climb a bigger mountain next time. So problems are a very useful challenge, but sometimes people's ideas develop without the problem. They develop much looser way. By the time you get to a problem, you already got halfway to the answer. You know, you focused on something. At the beginning, things are much more nebulous. And the nebulous stage is usually kind of more exciting because it's more has a greater potential. When you've got a problem, you either solve it or you don't solve it. When you're thinking broadly, your imagination is free.
Well, we have come to the end. At lunch we can discuss on God and on agnosticism. I have to say that it has been a pleasure to have you here all these days, and especially in this conference. The debate has been quite interesting. Bueno, quiero pedir un aplauso para el profesor Atiyah.